This series of PLC tutorial. Wish all you are well. In this tutorial I am going to discuss about how to implement different logic gates by using ladder diagram in PLC. I will explain on NOT gate, AND gate, OR gate, NAND, NOR, exclusive or exclusive NOR gate. Entering into the discussion, please subscribe. It is the only return from you to me, and also it will encourage me to upload more and more important tutorials. This is the symbol of NOT gate. In NOT gate, a single input and a single output. The equation of NOT gate Y is equal to A bar, where Y is the output and A is the input. The truth table of NOT gate: when the input is 0, output will be 1. When the input is 1, output will be 0. We all know how to draw the ladder diagram in PLC. This is the implementation of NOT gate. A normally closed contact has been used as an input. The address of this input is I0.0 and this is the output. The address of this output is Q0.0. What is the function of this normally closed contact? As this is normally closed contact, so it will be activated only when the field signal will come as logic 1. Now when the field signal is 0, then this normally closed contact will remain as it is, means it will be closed. So here result of the logic operation will be logic 1. Logic 1 means this will be just like short circuited. So power flow will be here from the positive power supply, and that power flow will reach to the output coil, and output will be logic 1. Now when logic 1 signal will come from the field, this normally closed contact will be activated and this will be open. When this will be open, here the result of logic operation will be 0. This is 0 means this will act just like a open circuit, so no power will come at the output coil Q0.0, so the output will be 0. Means when the field signal was 0, output was 1. When the field signal was 1, output was 0. So this acts just like NOT gate. Normally closed contact acts just like as an inverter. It just inverts logic level signal from the field. If field signal is 0, this result of logic operation will be 1. If field signal is 1, result of logic operation here will be 0. Before implementation of NOT gate, here I am explaining how PLC works with a very simple programming. Here one input switch has been used as the input and one LED has been used as output. Now this is a simple program. When this input will be logic 1, the output will be logic 1. This is the switch. When switch will not be pressed, it will produce the 0 signal from the field. When this switch will be pressed, it will produce logic 1 signal. So when this will not be pressed, then the output will be 0 or the LED will not be at glowing condition. When the switch will be pressed, then the LED will glow. This is a very basic function I am showing here to explain how the PLC works. Now see here, the switch is in 0 position. According to this ladder diagram, when I will press the switch, the light will glow. Now I am pressing the switch. See, the light has been glown here. And here from this power flow, full rung is having colored, means this input is logic 1, output is logic 1. Now I am sending logic 0 signal from the field. So I am again pressing this switch to make the field signal as logic 0. Say the output is off. Here say the full rung as well as the output has no color. Now I am implementing NOT gate. For implementing NOT gate, I have used a normally closed contact in this position. What is the present situation of this closed contact? What is the field signal? See here, input 1 is having true, means the field signal is coming as logic 1. See here, the input switch is towards the 1, means the input switch is now giving the logic 1 signal to this ladder diagram. So when this is logic 1, what is the output? Now output is 0, no color is here. See here the indication output 1 is false, means output is 0. So when input is 1, output is 0. Now I am giving the 0 signal from the field. The output should be logic 1. This LED will glow. For giving the 0 signal, I am pressing this. See, this is 0 signal. The LED is now glowing condition as output, and see the ladder diagram. This is 0, as this is normally close contact, so this is acting as a short circuit, and ultimately we are getting the output as logic 1. See here, input is false, means input is 0, but output is true. Now what should be the output when I will give logic 1 signal from the field? This LED will be in off condition. So to see that, I am pressing this switch to make it logic 1. Now see logic 1, the output is 0. See here, the output is 0. So we got the exact output as NOT gate. Now the same NOT gate we can implement by using a negation instruction. I am showing it. I will introduce a negation instruction here. Which type of contact I have used here? Normally open contact I have used here. Now I am inserting a negation instruction. Say this is the negation instruction. I have introduced this negation instruction. What is the function of this negation instruction? It will just act as an inverter. Means if the signal here is 0, after this negation instruction it will be logic 1. If the signal before this negation instruction is logic 1, after it will be logic 0. Means when the input signal will be logic 0, it will just invert to logic 1. When the input signal is logic 1, it will just invert to logic 0. So the full system will act as a NOT gate. Now see whether it is functioning or not. See what is the status of the input from the field. The status of input from the field is now 0. See here, input 1, it is showing false. So no doubt the input signal is 0. And what is at the output? The output is having colored. So this is no doubt output is logic 1. See here, the output is glowing. So the input from the field is logic 0. At that time we are getting output 1. Now I am changing the input. Just pressing this switch, it will produce the logic 1 signal from the field. Say this is logic 1 signal. Instantly the output is off. From here that this is colored. So this input 1, this is logic 1 signal here. Ultimately this negation instruction inverts it, and ultimately output is 0. So input is 1, output is 0. So this is functioning as NOT gate. So in any ladder diagram, we can use this negation instruction for inverting the output of combination of logic instructions. Next, coming to AND gate. This is the symbol of AND gate. The equation of this AND gate is y is equal to a dot b. This is the truth table. We will get the output as logic 1 only when both the input is logic 1. For all other case, the output is logic 0. This is the ladder diagram for the case of AND gate. What is happening here? For the case of 0, 0, as this is normally open contact, so here this will be 0, this will be 0, so output will be 0. As this is the AND gate, so both should be logic 1 to get the output. Otherwise no power will flow from the input side to output side. So only when this will be 1, again this will be 1, at that time only we will get the output as logic 1. All other cases the output will be logic 0. Now say output should be logic 1 when both the inputs are logic 1. At this position, first input is logic 0, second input is logic 0. We are getting output 0. Now I am changing first one to logic 1. Say first one is logic 1. Here say this is logic 1, second one is logic 0. We are getting output 0. Now if we change the both inputs to logic 1, then we will get the output. Now changing the second switch to logic 1, we should get the logic 1 output. See whether we are getting it or not. Just changing the switch to logic 1. Yes, the output is logic 1. So this is the operation of AND gate. Now explaining the NAND gate. There is a symbol of NAND gate. Output Y is not of A dot B, and according to De Morgan's theorem, this will be A bar plus B bar. So how to implement this? A is the input. This is A bar. This plus means this is OR gate. B bar. So this is B bar. The parallel inputs acts like a OR gate. So this is A bar, this is B bar, and both these two are in parallel having the OR gate. This is the truth table of NAND gate. For the case of NAND gate, only when both the inputs are logic 1, at that time I will get logic 0. For all other case, output is logic 1. Say I am explaining for first one, both the input are 0, 0. As both are normally close contact, so here it will be logic 1, here it will be logic 1. Ultimately, the output is logic 1. Similarly, for the case of 0, 1, for 0 this will be logic 1, but here this will be logic 0. This path is short circuited, so output will be high. Similarly, for the case of 1, 0, this path will be short circuited, output will be high. Now for the case of 1, 1, when this is 1, field signal is 1 for this input, output is 0, because this normally close contact acts just like an inverter. Again this is 1, this is 0, so both are 0, we will get output at 0. When both the field signal are logic 1, at that time we will get the output 0. For all other case, output is logic 1. In NAND gate, we should get logic 0 only when both the inputs are logic 1. For all other case, the output will be logic 1. See here, input 1 is having 0 state, whereas input 2 is having 1 state, and output is logic 1. See here, this is 0 state, this is 1 state, we are getting logic 1 out. If we change second switch to 0, at that time also it will be logic 1 output. I am changing it to 0, still logic 1 output. Only we will get logic 0 output when both switches will be logic 1. Now making the both switch logic 1. This is logic 1 and changing the second switch logic 1. While I will change this to logic 1, the output should be logic 0. See here. Yes, the output is 0. When both are logic 1, see here, this is logic 1, we are getting output as 0 signal. So this is NAND gate. Next, OR gate. This is the symbol of OR gate. The equation y is equal to a or b. So this is the OR gate. In the ladder diagram, these two inputs will be placed in parallel. So this is one input, there is another input as parallel. And what is the truth table? If any one of this input is logic 1, then the output will be logic 1. When the both input will be logic 0, then only we will get logic 0. So we will get logic 0 only when both input is logic 0. For all other case, we will get the output as logic 1. Now say, here output will be logic 0 only when both the inputs are logic 0. In all other cases, output will be logic 1. See, input 1 is logic 1, input 2 is logic 1, we are getting output as logic 1. From the ladder diagram, we can see this is logic 1, this is logic 1, output is logic 1. Now changing the first input to logic 0, output should remain logic 1. See, changing it to logic 0, output is still logic 1. Here we can see the input 1 has been changed to logic 0. Still we are getting the logic 1 output. Only we will get the logic 0 output means the LED will be off condition when both the switches will produce logic 0 signal. Now first switch is logic 0 signal. I am making this input to logic 0 signal. Just pressing this one, the light should be off. Say, yes, light is off. So when both switches are in logic 0 condition, then the output is logic 0. So this is OR gate. Next, coming to NOR gate. This is not of OR gate. So this is the symbol, output A dot B whole bar. Ultimately applying De Morgan's theorem, we will get A bar dot B bar. So this is the AND gate of A naught and B naught. So the ladder diagram will be, this is A naught, this is B naught. A naught means this is normally close contact of the input A. This close contact is the representation of input B. Both are in AND gate, so this is in series circuit. What is the output? we will get the logic 1 only when both the inputs are logic 0. For all other case, output is 0. See from the diagram also, at the output if we want to get logic 1 signal, no doubt the result of logic operation for this input should be logic 1 and result of operation of this input should be logic 1. So when this will be logic 1, this will be logic 1. As this is the normally closed contact, this is normally closed contact, no doubt the field signal should be logic 0 for the both case. When the field signal from the both input will be logic 0, then here it will be logic 1, it will be logic 1, and ultimately at the output we will get logic 1 signal. Now see, here output will be logic 1 only when both inputs will be logic 0. See here, input number 1 is logic 1, input number 2 is logic 1, output we are getting logic 0. See, we are getting output as logic 0. If we change input 1 as logic 0, at that time also the output will remain as logic 0. See, output is logic 0. Output will be logic 1 only when both the inputs will be logic 0. Now first input is logic 0, I am changing second input to logic 0. When I will press this switch, then instantly the output LED will glow. Now see, pressing this switch. Yes, output is glowing. So when both switches are in logic 0 state, at that time only we got logic 1 output. See, this is 0, this is 0. As this is normally closed contact, it acts just like inverter. So when this switch is 0, this is logic 1. When this switch is 0, this is logic 1. We are getting output as logic 1. So this is NOR gate. Next, XOR gate. This is the symbol of XOR gate. I is A XOR B, and after simplification it will be A dot B bar plus A bar dot B. So this is the OR gate of the product A dot B bar and A bar dot B. So A dot B bar implementation of this is A, normally open contact, B bar, this is B bar, as this is bar, so this is normally closed contact, and another one A bar, this is A bar, this is B, so this is the normally open contact. Now result of these two and result of these two are in ORing, means these are in parallel combination. Now what is truth table of this XOR gate? Here we are using two inputs only, so we will get logic 0 output when both the inputs are in same status. See, for the case of 0 0 we are getting logic 0, for the case of 1 1 we are getting logic 0. In all other cases we will get logic 1 signal. We will get logic 0 signal when both inputs are in same state. Now say, in XOR gate, when status of both inputs will be in same state, then output will be 0. In all other case, output will be logic 1. Now say, input 1 is having 0 state, input 2 is having 0 state. We are getting output 0. If we change any one to logic 1, then output should be logic 1. See, I am changing first one. Yes, output is logic 1. See here, output is logic 1. Now if both switches will have logic 1 state, again the output will be logic 0. Input 1 is having logic 1. I am changing this input to logic 1 state. When I will change this input to as logic 1 state, output will be off. Pressing this, yes, output is off. So when both the inputs were 0 0, then we got the 0 output. Now when both inputs are logic 1 and 1, we got output as logic 0. So this is XOR gate. Now this is XNOR gate. This is the symbol of XNOR gate. This is XOR with a NOT gate. We can implement this XNOR gate by using this equation, y is equal to A dot B plus A bar dot B bar. So this is OR gate of A dot B and A bar dot B bar. So this can be implemented as A dot B. This is the product. So this is A dot B. Next one, A bar dot B bar. This is A bar dot B bar. These two are in parallel circuit. Now what will be the output? This will be just reverse of XOR gate. As in this case we are using two inputs, so we will get logic 1 signal when both the inputs are in same state. In all other case the output is 0. We can check it from here also. For the case of 0 0, this will be logic 1, this will be logic 1, this will be 0, this will be 0. So through this path output will be logic 1. For the case of 0 and 1, this will be 1, this will be 0, this will be 0, this will be 1. So for this line, this is open circuit, for this line this is open circuit, so output will be 0. The similar thing will happen for the case when the input 1 is 1 and input 2 is 0. What will happen when both inputs are logic 1? This will be 0, this will be 0, this will be 1, this will be 1. So through this path the output will be logic high. Now say in XNOR gate output will be logic high when both the inputs will be in same state. Means when both the inputs will be logic 0 and 0, or both the inputs will be logic 1, then we will get logic high in output. Now see here, input 1 is logic 1 and input 2 is logic 0. So in this case we are getting logic 0 as output. See, LED is not glowing. Now if we change this input 1 to logic 0 condition, then both the inputs will be in 0 state. At that time the LED should glow. Pressing input 1 to change it to 0 state and see whether LED is glowing or not. Pressing, yes, LED is glowing. Now both switches are in same state, which is 0, and we are getting the output. Now if we change this second switch to logic 1, then first switch will be logic 0, second switch will be logic 1, so the output should be 0. Say, yes, output is 0. Now if we change both the switches to logic 1, say second switch is logic 1, now if we change the first switch to logic 1, then both will be in logic 1 state and output should be logic 1, means the LED should glow. Pressing this one, yes, the LED is glowing. Here we are getting the output. So when both switches are in same state, either 0 or 1, we are getting logic 1 as output. So this is XNOR gate. So in this discussion I have explained how to develop different logic gates by using ladder diagram in PLC. I have explained about NOT gate, AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate. I have implemented all the gates with ladder, as well as I have tried to explain it with visual graphic display by using switches and lights. I think we got an idea how to develop the ladder diagrams in PLC. Please subscribe, put your comments and queries in comment section.